There's about 23 participants. We'll go ahead and get started. Tonight's webinar, first of all, everyone can see the presentation. It says live webinar, power, delta versus Y, phasor diagrams, three-phase circuits, leading versus lagging. Can everyone see that okay? And is it full screen? It should be maximized. Everyone's saying yes? Good, good. Before I get off the webcam and start solving problems, the goal of tonight's webinar is I want each of you to have a solid handle on all of the power formulas. I don't want anyone to get confused with delta versus Y. So we're going to be taking an in-depth look at the differences between delta versus Y, the phasor diagram specifically for both, which I find tends to be a sticking point for a lot of people. And you'll find that at first, a lot of people want to run from phasor diagrams, right? They get scared of it because they're just not familiar with it. But I find that once you have a solid understanding of it, it actually is a tremendous help, right? It's one of the best tools that we have available to check our work, to make sure we're not about to embark in a set of calculations that are really wrong or far off. So you'll find that after tonight, if you don't have a solid grasp on phasor diagrams, you'll find that once you get comfortable with them, you're going to start using them more and more and more. And not only that, when you get to a certain set of problems where you're not sure what to do, I bet you're going to be able to draw those phasor diagrams and you're going to be able to follow the correct steps to get to the answer. So I really think that is going to be the highlight of today's session. After that, we will talk about three-phase circuits, specifically how we use delta and Y together. So we'll be looking at a delta source and a delta load, a delta source and a Y load, a Y source and a Y load, and a Y source and a delta load. We'll talk about how to go to the equivalent single-phase circuit from there, how to solve for all of the various variables. We'll work problems backwards and forwards using a variety of different formulas, essentially so that no matter how you get presented with a delta and Y three-phase circuit, you'll know immediately how to attack it from here on out. And then we will touch briefly, I didn't have it included up here, but we will touch briefly on impedance transformation. So if we have a three-phase Y load or a three-phase delta load, how we go back and forth between the two and when we need to do so. So I think that will be a really good talking point. And then if we do have enough time, I will touch briefly on leading and lagging. And I saved that for the end because I'm hoping by now, the vast majority of you, it'll be nothing but a review. I'm sure a few of you still have a few sticking points with leading versus lagging, but I feel comfortable that there's enough videos and modules available on the course that you can work that on your own time. Even still, it does tend to be an area where students get questions wrong. So I'm going to save it for the end. That way, for everyone that it's new, if we don't get to it, for everyone that has a handle on it, it won't be a waste of time. So before we begin, does anyone specifically have any confusing areas or any parts of power, delta versus Y, phasor diagrams, three-phase circuits, and leading versus lagging? Let me know in the chat. Let me know if there's anything that you've been scratching your head with recently, or maybe just some areas that you've had a hard time with, maybe some questions that you get right sometimes, but then you don't get them right other times, you're not sure why. Go ahead and type that in the chat now. That way, when we go into this, I'll be able to keep those in mind and hopefully address those specific examples. Okay. So not seeing a whole lot, so I am going to assume that everyone is masters and experts at this, which means I get to throw the hardest questions at you. All right, Eric just said, I just finished the watt meter section and I found I was a bit confused on the VI and I'm guessing that's line voltage and phase voltage relationships for 3 and 4 wire meters. For 3 wire meters, it says line voltage magnitude. So Eric, if we have time, we might be able to talk about watt meters. I think that when we talk about delta and Y three-phase circuits, a lot of that will kind of clear up your questions. I don't have any material prepared tonight specifically for watt meters, but watt meters is probably one of the sections I'm going to talk about in one of the upcoming classes because it does tend to be a confusing bit. So how about this, Eric? If what we talk about, if you still have issues with watt meters, feel free just to send me a private email and I'll be happy to talk to you about it one-on-one. But biggest thing with watt meters is really all you're looking at are separate current and voltage readings, right? So you can almost ignore watt meters and treat them like three-phase circuits as long as you know the 2 watt meter and 3 watt meter method. So, but if you still have questions with that, just shoot me an email. Omar said, when question is asked about adding Q to correct power factor, I am confused if the sign is a negative or positive at the end. Omar, since that was with last week's webinar, I don't want to take too much time tonight. Feel free if you want to hang around after the webinar is done, Omar. I'd be happy to answer that and do a couple examples live on the whiteboard here on the screencast. But I don't want to tie up everyone's time. So me and you can stick around after the webinar is done, and we can do a couple examples on the screen because that's a really easy one to address. Or just shoot me an email, and just the same with Eric. I'll address that with you one-on-one. Ega said, when we have a delta load, do we convert to Y when we try to solve for voltage and current? Good. Okay, so great, Aegis. That's actually precisely one of the areas that we're going to talk about today. So I'm glad you asked that, because that lets me know we're gonna hit that right on the head. So we will definitely talk about when to convert delta loads to Y loads when we're solving for specific voltages. Kahina said, conversion of delta to Y and finding impedances and finding power. Yep, we will definitely address that. So essentially everything we're talking about is leading up to precisely that, right? We're going to talk about our power formulas. The difference is between delta and Y standalone, right? Just delta source, delta load, and a Y source and a Y load. And then we're going to discuss the phasor differences, especially we're going to talk about the phase values versus the line values for voltage and current. And then once we understand all of those mechanics, we're going to bring them all together and talk about exactly how to do that, to find that when we use three-phase circuits. So good. I'm glad that's an area of question for you. Alex said, can you please explain when to consider the sign, plus or negative for current and voltage for an impedance? Sure, I would be happy to. In fact, Alex, when we talk about impedance transformation from delta versus Y, if I forget or if I don't bring that up, please jump in the chat and remind me. I would be happy to explain that when we get to that part. We'll also explain that for source too. So maybe that wasn't part of your question, but it's also kind of the same area. And I think explaining both of them together at the same time will really clear that for you. So absolutely, we can definitely talk about that. All right. Anyone else? Any other kind of head scratchers or areas we're not clear about relating to here? Tony said, when do we use angles and when not? Perfect. We can talk about that. I think the best time to talk about that is when we talk about the three-phase circuits, and I'll try to sprinkle that in too when we're talking about the other areas. Tony, feel free to jump in the chat if we get to any parts of this live class when I'm not using the angles or when I am. Feel free to jump in the chat and stop me and say, hey, why are you using the angle? Or hey, why are you not using the angle? And to give you a quick glimpse, typically when we're only dealing with magnitudes, say, for example, the question is asking you to find some current, and all of the answers like 200 amps, 500 amps, 350 amps, and there's no angle for that current, then you can pretty much dump the current and just work in magnitude, since the angle is essentially just the direction, right? It's the angular direction of that phasor compared to the other phasors. So a lot of times if the answer isn't specifically asking for that, then you don't need to carry the angles in your calculations. Sometimes it will affect the magnitude though. So when in doubt, use it and then just drop it at the very end. And other times they're not going to give you the angles. So be mindful of that too. And I will try to talk about that in the three-phase circuit section. Alex said, how to spot red herring data? So great question. I wish there was an easy way, right? I wish all of the red herring data in a question was highlighted red or had like a stick figure next to it. Unfortunately, right, that's not the case. The best way is to be really comfortable with your relationships and your formulas, because you 100%, and I'm glad you asked that too, because I can address it with everyone in the room. So everyone that's here, definitely know that you will absolutely have a couple of questions where you have data given in the question that you don't need to solve. And if you try to use it, you're going to end up going down a rabbit hole, right? You're going to end up solving for something that you don't need to. And so to answer your question directly, Alex, there really is no clear way. Arturo, I think you just turned on your video. Let me turn it off for you. Alex, there really is no real clear way. You just have to be comfortable with your formulas. Know exactly what missing variables you need to solve the answer, and then know what formulas to get those variables from, and then just try to steer in that direction as much as possible. Miguel said, when to use the square root of 3. So Miguel, we will definitely talk about that when we're dealing with the phase versus line values for phase or for voltage and current when we're dealing with delta and Y. If is that what you're referring to? A lot of times that trips people up. So if that's what you're referring to, we will definitely talk about that tonight. And ZL said, in general, can you tell us what formula and information is best to memorize? Sure. And what we can just know where to look in references. So who can tell me really quick? And I might not have said this directly live on a webinar, but I think I allude to it in a couple of my videos. This will help me answer ZL's question. Who can answer me in the chat? When you don't know what to do or when you're stuck, what are the two formulas you always go back to? And if you only want to guess out one of them, that's okay too. Go ahead and someone guess in the chat. Alex said Ohm's law, Selena, Beatrice, Greg, all correct answers. Yep, Kahina, V equals IZ. That's the first one. Great job. So for everyone that wasn't sure, I would say the number one thing to go back to is Ohm's law. That's going to be one of the most reoccurring. ZL, you're close. ZL said P equals to VI. Beatrice, you're also close. Isn't that formula really, isn't that the real component of a more complex, keyword complex formula? Bingo. Zach J said S equals to VI. And Beatrice, you get the gold star for tonight because you included the conjugate. Beatrice said S equals to VI conjugate. Absolutely. So whenever we don't know what to do, if we're stuck, and I'm even going to draw on the screen here. So anytime, and this is exactly what I do when I'm solving problems, when I'm looking for ways to check my work, right? Because a lot of these formulas have circular relationships, right? They go round and round in circles, and there's different ways we can prove them since everything is related. It's also a great way to check your work. So you always want to go back to V equals to IZ, and that's Ohm's law. And of course, these are complex vectors, right? So I'll include my vector hat. And the other formula is single phase power. S apparent power equals to VI conjugate. We can even say these are the phase values, right? Does everyone agree? So these are the number two formulas that you should, by now I know everyone has these memorized. It's the different variations of these that get difficult. Who here in the chat, go ahead, let me know who has started the Power Fundamentals Bootcamp, who's about halfway through, and who's finished it. Who can tell me in the chat? I've seen a lot of you have signed up. Good, a lot of people are saying I finished and completed 70%, just started a third of the way through. How's everyone liking that so far? Have you guys found that valuable? Have you learned a few things that maybe were elusive before? Selena said helpful. Good. So a lot of you have been finding that helpful. My number one goal with that is, so these formulas over here, Ohm's law and our apparent power formula, there's so many different ways those can be expressed depending on if it's single phase, three phase, if we're just using the voltage, if we're just using the current. Seeing how all of those play together, especially with just those two with Ohm's law and apparent power, I think that's really eye-opening. And the best part about that is, and this is to answer the question about what to memorize and what not to memorize, as long as you can derive that, as long as you're comfortable deriving it, really those two are just about the only two things you need to memorize. Of course, there's going to be a few things here and there, but essentially 80% of what you need to memorize is just Ohm's law and apparent power. Someone else said valuable. The added case study is a good example. Good. The person that case study came from that sent it in today is actually in the chat. I won't say anyone, but I'm glad, ZL, I'm glad you enjoyed that case study. That case study was so good because if you followed everything to the letter, you were likely to get it wrong. It requires you to think critically and draw a diagram to realize that we had to use slightly different variables than what you might consider at the very beginning. So good, I'm glad you found that variable. Or I'm glad you found that valuable. Okay, good so far. It's about 8:50. Any more questions? If not, we will get right to it. So I'll wait just a few more minutes. Arturo said, if the problem does not specify if it is delta or Y connected, which one should we assume? Great. I am so happy you brought that up because that is 100% something I want to address. And it's a lot of times people get stuck on delta versus Y, right? They're like, well, the problem didn't say delta, didn't say Y. How do I know? So Arturo, I'm going to talk about that in three-phase circuits. Please, 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 since I'm juggling a lot right now in my mind about what I want to teach and what my goals are for everyone to go home with today. If I forget to bring that up, Arturo, please stop me in the chat and just say, hey, Zach, can we talk about this? Even copy and paste it. I just don't want to miss that. That goes for everyone else too. All these questions, I'm going to try to get to them. If I forget or if I'm moving on to another topic, bring it up. That's definitely something we can talk about in three-phase circuits, and it'll be really valuable. All right, anyone else? How's my audio quality? Can everyone hear me? Am I loud and clear? Omar said good. ZL said good, good, good. Okay, good. Yeah, it should. Sometimes it's a really good mic. One of the things I'm a big stickler for is good audio quality. Sometimes the gain is either up too high, and I can't tell. I don't like to use headphones when I talk. So sometimes if the gain's too jacked up, it buffers out. So if that's a problem, just let me know. We'll make sure we keep it good. Okay, it's 8:51. I don't want to waste any more time. So I will hop off the webcam now, and we will get right into it. Okay, good deal. So can everyone see the presentation should be full screen still? Yep, good. Okay, first thing I want to talk about is our power formulas. And here's where I want all of you to get involved. So just like last time, this is going to be a really engaging live webinar. The goal is this is not a TV show, right? This is not a passive sit back and hope to kind of absorb stuff. We're going to consider this an active learning environment. So I'll be stopping every step of the way and gauging everyone's reactions from the chat. So the first thing I'm going to draw is this. I want everyone to tell me what's wrong with this. This is a big mistake a lot of people made, and I'm hoping that everyone can answer me correctly. If you've been through the Power Fundamental Boot Camps, this should be a no-brainer for you. So let's say I'm solving for three-phase power, okay? So we'll say three-phase apparent power in volt amps. And let's say my line voltage is 480 volts at 0 degrees. So we'll say that's our VL. And let's say our line current is, we'll go with, let's say 100 amps at negative 30 degrees. We'll say it's a lagging system. So if I was asked, find the three-phase apparent power in volt amps. Of course, we know that's our S3 phase. If I was asked this on the PE exam, what would be wrong with doing it this way? Would this be correct or would this be incorrect? So can I say my three-phase apparent power? I know it's going to be the square root 3 times VI conjugate. So I'm going to carry it out and say my three-phase apparent power is the square root of 3 times, I know I need my line voltage and my line current. So I'm just going to put 480 volts at 0 degrees times 100 amps at negative 30 degrees. So I'm going to carry that out and say, okay, I found my three-phase apparent power as, I'm going to say the square root 3 times, that would be what, 48 kVA, I think, if I did that right, at an angle of minus 30. So is this correct or is this incorrect? Who can help me out in the chat? Raymond said incorrect. Cynthia said not negative 30. Greg said angle should be plus 30. Beatrice said not 30. Craig said conjugate. Okay, I did forget that conjugate. Let me change this to plus 30. How about now? Now is it correct? So I forgot the conjugate, that pesky conjugate, right? It gets us every time. So we know we have a negative current angle and our conjugate's here. So this time I went ahead and I changed that to plus 30, but everything is correct. Is that true? M. Walker said magnitude only. She's the, M, I'm hoping that stands for Mary. I'll say M. Walker is the first person to answer this correctly. Sarab said 48 kV. No, Sarab, we are solving for three-phase apparent power And we know when we multiply volts times amps, we'll get our volt amps. Kahina said conjugate and needs to put in complex form. So okay, so we got the conjugate. Technically, this is complex form. It's complex polar. Raymond said this approach is incorrect in case of single phase. Raymond, I'm not too sure. Raymond, can you expand on that? So who else can help me here? M. Walker is the first one to hit the nail on the head. Who else can tell me why is this incorrect? And the reason why I'm starting out with this is about 80% of what people do when they first start to study and they first start to use three-phase power formulas. 80% do this, and this is 100% the incorrect approach. So who can tell me why? Raymond said the angle is actually theta V minus theta I and not I conjugate. Well, we did say our theta V was 0 degrees, right? So we still have 0 degrees minus 30 degrees would be plus 30. Kahina said convert to three-phase. Kahina, can you tell me more what you mean by that? Miguel said multiply by 3, not square root of 3. No, not quite. How about this? M. Walker, you are the first and really only person to hit the nail on the head in the chat. M. Walker, you want to tell me in the chat so everyone can see what we're doing right, what we're doing wrong, and why only the magnitude is correct? And Walker said, need theta S or theta Z. Okay, so if this is not theta, so M. Walker is saying this is not theta S. So if that's not theta S, how do we find theta S? Eric said, S for three-phase, magnitude brackets. Eric, you are a champ tonight. That is absolutely correct. Kana said the conjugate is for one phase. Yep, so I'll say that's for single phase. So let's look at this another way. It looks like we've got about the same kind of group of people that are pretty much catching on, and the rest of the chat is quiet. So I'm guessing a lot of people are scratching their heads. Let's look at this. We know that, and I'm guessing that the people that aren't sure, I would advise you to work your way through that power boot camp. This is probably one of the biggest reasons why I did it. So I'm going to draw the correct version of this. So the correct way would be we can use that formula essentially, but only for magnitude. And I'll talk about why. So the correct way would be, this would be our three-phase magnitude, right? These brackets right here mean it's just the magnitude, right? So if I were to draw a phasor diagram, it would just be this length, but no angle, right? Everyone comfortable with that? So we could say our three-phase magnitude is equal to the square root 3 times the magnitude of our line voltage times the magnitude of our line current. That's perfectly okay. And this would give us volt amps. However, like a few of you said, our angle's wrong, right? Plus 30 does not equal theta S. So whether we're dealing with three-phase or single phase, our theta is the same. So our theta, I'm just going to draw theta is the same theta that we use for theta three-phase, and that's the same theta that we use for single phase. And really, that actually ends up equaling our impedance angle. So how do we find this? Well, theta is really the difference between our phase voltage angle and our phase current angle. And a sneak peek, we're going to talk about this when we get to the delta versus delta and Y section. For a for a Y system, our line voltage is actually going to lead our phase voltage by 30 degrees. So by using the theta of our line voltage right here, we're going to come up with a wrong version for theta S. So how can you, or when are you going to expect to see this? 9 times out of 10, if a problem is going to give you, let me just go to a new page. 9 times out of 10, a problem is going to give you two things. It's going to give you your three-phase power in volt amps, and it's going to give you your power factor. So what you can do is, and let me draw the brackets. So it's going to give you just the magnitude, right? Magnitude only. So in order to avoid that trap, to get the true complex apparent power, you take the magnitude, but you want to always find the angle from your power factor. Does everybody see that? Really take a look at this, because 80% of people, they get so used to writing this. And this is why notation is so important. This is why almost always you're going to see me write three-phase or single phase. I'm going to always try to draw my vector hat, or I'm going to show my magnitude brackets when it's just a magnitude. And I really want to encourage everyone to get into that habit. I promise you, those of you who don't get in that habit, there's going to be a handful of problems you're going to get wrong, because just from a simple mistake. So one of the easiest way to improve your score, and you'll hear me preach about this over and over, is make sure you're always drawing your proper notations. So let's look at a few of the other correct ways. So I'm going to say this is correct. So a few of the other correct ways is single phase complex apparent power is our phase voltage and our phase current conjugate. That's perfectly okay. Our three-phase power is always going to be 3 times our single-phase power for a balanced system. In other words, when our phasors are equally spaced out and the magnitudes are all even. So that's perfectly okay too. So you can always expand that. And I won't go too far into detail on this, because again, all of this is in the some of the beginning of the power bootcamp. I just want to make sure we do touch on it tonight for those of you that haven't had a chance. Okay, so this is all perfectly okay. So you can get your magnitude, right, would be 3 times your phase voltage magnitude and your phase current magnitude. And here your angle would be theta VP minus theta theta IP, right? So our phase voltage and our phase current, right? And this is minus because of the conjugate. So this is also perfectly okay. So please be very careful. Be aware that the square root 3 formula, the one that we are all most familiar with, is only for the magnitude. So please don't make the mistake of using the complex phasor values for your line voltage and your line current and using the square root of 3 and trying to get your theta out of that as well. You're going to end up with the wrong value. So everyone, this is just something I really want you to be mindful of. Okay, I'm looking at the chat. Any questions with this right here, with what we did? And I'm not going to get into the I squared Z or V squared over Z equations. That won't be for tonight. Any questions at all? I'm not seeing anything in chat, so I'm going to assume you're all experts and masters, and I will move on. Okay, let's talk about why systems. Okay, we'll talk about a Y source and a Y load at the same time. So let me draw a Y source. Will look something like this. Not perfect, but it gets the point across. So this is going to be our source, and this is going to be our load. These two aren't connected, by the way. I'm just, we're going to talk about them individually. And then when we get into the three-phase circuit section, we'll talk about like a YY system. Okay, we'll say this is our Y load. And here's a great, actually, we'll talk about those polarity, the plus and minuses for the impedance. We can talk about that here too. Okay, so we will arbitrarily just assign our A, B, and C. And I'm going to go ahead and pick another color too, because I think it stands out a little better. So these are voltages. Everyone's comfortable, of course. Those circles are voltages and the squares mean impedances or a load. So that's source, this is load. Okay, I'm going to go ahead and pick red. We will say that this is A phase, this is B phase, this is C phase, and we'll go ahead and say the same thing for a load. So we'll say this is A phase, B phase, and C phase. All right, what's the first relationship that comes to mind when we deal with Y systems? Go ahead and shout it out in the chat, loud and clear. What's the first thing that comes to mind with a Y system? What's the one relationship we all know that we're the most familiar with when dealing with Y? Tony said same current, sure. Zach J said I phase equals I line, sure. Beatrice said I phase equals I line, sure. Okay, bingo. Eric got it first. The one I was looking for is VL, our line voltage. I'm going to make sure I draw the brackets here. We'll just talk about the magnitude so far. So our line voltage, we know the magnitude is 3 times greater than our phase voltage. And we know that means that our phase voltage magnitude is the square root 3 times smaller than our line voltage. So be really careful when we see things like this. I'm going to draw over here to the left. When we're talking about our I line equals I phase, I'm not a fan of saying this because I feel like it leads to people getting the problem wrong. So what I'm about to talk about, if this confuses you, just ignore it and go back to this relationship. But I think a few of you, this is really going to help. Instead of thinking that your line current and your phase current equals one another the other, it's really, you only have one current, right? Because the thing is, when we solve for that line current, what they call the line current, since it's really the phase current, in my opinion, the best way is to just think of it as it's your Y current. You really only have one current for your Y system. Because depending on, sometimes people will use the square root of 3 incorrectly when they're trying to solve for either the phase or the line, and they're going to get the wrong problem. So if it helps you to think of this way when you're dealing with Y as just having a single current, you can even say I subscript Y if it helps you. I would advise you to start thinking about it in that way. If that confuses you, then just go back to that relationship and just stick with what works for you. So those are the two biggest things. How about this? Over here on my source, who can tell me what direction is my current going in? Really easy. What direction is my current going in each phase? And this isn't a trick question. We know that AC currents are going to alternate from positive to negative, or they're going to be kind of changing direction depending on where exactly they're at in their cycle. But when we're analyzing a circuit and we're just analyzing at a snapshot in time, Craig said out. Sure, I'll accept that answer. Kahina said positive to negative. Okay, I'm going to stop right here. And Kahina, I want to address that directly. Be very careful. So Kahina said positive to negative. So Kahina said source to load. Okay, that's true too. Kahina, your answer, when you said positive to negative in the chat, where is my positive and negative on my source? How about, I want to make sure I address that correctly because you need to be careful with that thinking. So Kahina, let me know, you said positive to negative for the direction of our current. Where's my positive and where's my negative? Because it's actually going to be the opposite relationship for a source. And this relationship is really going to help you when we talk about delta because you'll see that the phase currents and the load currents are in opposite directions. Kahina said N to A or A to B. Okay, Kahina, I will accept that. I want to be careful because let's look at this really quick. So if this is our phase voltage, we'll say this is our A to neutral, right? That's our A phase voltage. The polarity for this voltage right here is going to be positive up top, and it's going to be minus at the star point, at the neutral point. So actually our current on a source is always going to flow from our negative polarity to our positive. And this is true for any source. I'm gonna draw that down here. So a source, our voltage polarity, our current is going to be in the direction of minus to positive. And the opposite is true for the load. I think maybe it was Alex, or I forget who asked in the very beginning. Someone was asking about this in the beginning. Our load, so our source, we have a generated voltage, right? On our load, we actually have a voltage drop. So our load voltage, if we have plus V minus, our current is going to go from positive to negative in reference to our voltage. And the best way to think about that is if I have a current, when a current enters, right, it's a current is the actual load in amps that this impedance is going to draw. As that impedance draws, I'm trying to draw a little over here. Okay. As this impedance right here, if we just want to single this one out for a second. So as any impedance draws a load in amps, it's going to have an effect of producing a voltage drop across that impedance, positive where it enters and negative as it leaves. The opposite is true for a source. As a voltage is generated from a source, it's going to leave the positive terminal. It's actually going to go in the orientation from negative to positive. This is true for all sources and loads, regardless if it's three-phase, single-phase. An easy way, if you ever forget in the heat of the moment in the exam, always draw, let's just draw a single-phase equivalent circuit. Everyone's real familiar with this. I bet most of us took this in college quite some time ago, but we know that our voltage source looks like that. We know our current goes in this direction, and we know our voltage drop is here. So just like before, we're going from negative to positive for our current direction for our source, and then our voltage drop and our current, the voltage drop is going to be positive where we enter that impedance and negative where we leave it. So if you ever kind of have a hard time remembering, just draw it out. You can look at these two relationships. That's true for any kind of source or load. All right, so we got our current directions. I'm going to go ahead and fill that in for the others. So we'll call this IA. We'll call this one IB. And we'll call this one IC. Fair enough. Who can tell me what voltage this is? Real easy. Give me a question. What voltage is this right here from our A terminal to our B terminal? Go ahead, let me know in the chat. What should my subscript be right here? Great, seeing a lot of answers. Beatrice, Beatrice got the answer I'm looking for. So we'll call this VAB. Keena said square root 3 VAN. Yep, that's true. Not exactly the answer I'm looking for. Craig, Omar, and Rel. Yep, 100%. This is the answer I'm looking for, VAB. So typically anytime we use subscripts, we're also indicating polarity here too. For voltage, the first subscript will be our positive, and the second subscript will be our negative. So let's look at this voltage right here. I'm going to just draw it a little bit off to the left. So if I have a positive reference here and a negative reference here, who can tell me in the chat? Another really easy, give me a question. What voltage is this? What's my subscript? Kahina, bingo, VBC, great job. VBC. And we'll just do it one more time. Again, really easy, give me a question. Or who can tell me what is my voltage if we have a positive reference at C and a negative reference at A? This, of course, is going to be my V. Who can tell me in the chat? VCA, right? Perfect. Real easy. Remember, positive first, negative second. Okay? Now, trick question. What direction, if I wanted to draw a negative IB, what would that look like on my source? What would negative IB look like? Would it be over here? Would it be over here? Who can tell me? Keena said IBA. Let's just look at, since we don't have anything connected to the circuit yet, Beatrice said beta neutral. Perfect. Yep. So really, everyone comfortable with a negative sign? When we multiply it by a current, all we're doing is changing the polarity. And when we change the polarity, all we're doing is changing the direction. So that would be minus IB. Okay. Craig said along B, leg towards neutral. Perfect. Good job, Craig. Yep. Okay, let's see. What else can we talk about this Y source? So we know this is our neutral voltage. I don't need to draw out the neutral voltage for the other phases, do I? I think we're all comfortable with that. All right, let's look at our load. Pretty easy. Okay, here's a great question, and I would like everyone's participation in the chat. So how about this? Tell me what's wrong with this. I'm going to say each one of these impedances is the same value. So they're just going to equal to Z. Next, we've got a voltage. We'll just call this plus, minus. What would this voltage be? What would my subscript be for this voltage right here? If I had a positive reference at C and a negative reference at B, what would this voltage be? Perfect. VCB. Okay, good. And as a quick aside, what if I did minus VCB? We could say that would be equal to a positive what? A minus VCB would be a positive. Yep, Zach and Sarab, good job. Would be a positive VBC. Perfect. Okay, so I'm looking for someone to tell me what is wrong with this approach, because this is another approach that people do quite often when they're new to three-phase power circuits. It seems right at first, but as we get further into it, we'll see why it's the wrong approach. So I know my voltage across VC from C to B. I know this voltage. And I know I've got two impedances right here and here. So can I use Ohm's law? Let's look at this current. Say, I'm just going to say this is I. I know Ohm's law, right? That's one of the things we always go back to. Ohm's law is V equals to IZ. And we'll say these are all complex impedances. This is a complex current. This is a complex voltage. So if I wanted to solve for my complex I can just say I equals complex V over complex Z. So I know, right, the total voltage across this is VCB. And look at this, I've got two impedances in parallel in the direction of that current. Can't I just say that's Z plus Z or 2Z? Who can tell me what's wrong with this? I'm going to write incorrect. That way, if anyone downloads these notes, they don't get led astray. Kahina said no. Need phase voltage for each impedance. Good. Greg said doesn't count for the current going into a phase. Perfect. Greg, that is exactly the answer I was looking for. Alex said KCL. Bingo. Another valid answer. So everyone sees this. This is incorrect. When we talk about the three-phase circuits, that's when we'll go into pretty much splitting up line voltage into phase voltage and solving for all that stuff. Okay, so I think I feel pretty good here. I want to move on to the phasor diagram for the Y systems. Mary said, how do you select the voltage references? So Mary, it depends on the polarity. So what if my VBC, how about we'll do it over here? Because we're usually used to assigning the voltages to the source. So how about this? If my line voltage was 480 volts, right, for three-phase system, and it was positive, a positive ABC system, if I asked you to tell me what was VCB, right, we would know it would just be minus V, V, okay, that's fine. So this is VAB. Sorry, this kind of tripped me up really quick. So if my voltage from across A to B is positive 140, and I asked you, okay, what's my voltage for VBA, right? It would be minus VAB. So when we are signing references, and let me know if you're not talking about the polarity. When we're signing the polarity, the positive end will be at the positive end, and if we're incorrect in our assumption, then we simply just multiply it by -1. Mary, did that answer your question, or were you referring to the subscripts? Okay. Mary said, how do you, okay, so she said, okay. All right, I'm going to move on to the phasor diagrams for Y. Does everyone feel comfortable with what we just did for the source and for the load? This is kind of all we can really talk about, I think, from where we're at. So I'll scroll down. Y phasor diagram. Again, a lot of people run from this. I don't think it's a big deal. Once you get real comfortable doing this, you'll see why it's really a blessing. It's really going to help you derive things on the fly. It's going to let you check your work. It's going to let you know if you're going down the right path. So let's just say our phase voltage. Actually, we'll start with this. I'm going to say that this right here, at this particular moment in time that we're looking at, since phasor diagrams, right, they're always rotating, we'll say this is a positive ABC system. So our phasors are rotating counterclockwise. I'm going to say this is my A phase voltage, all right? So my A phase voltage has a magnitude of the phase voltage, and it's at an angle of 25 degrees. And I'm just going to draw a Y source for reference out here on the side because, hey, I like my references. They help me a lot. So we'll say this is A, B, C. This is my neutral. Who can find for me on this phasor diagram, where would my plus VCN be? So this phase voltage right here, where would that be on this phasor diagram? Greg said 145. Anyone else? Anyone agree or disagree with Greg? Anyone not sure why? Kahina said 120 plus 25. Good. Tony, good. Alex, good. Jonathan said no idea. Craig said agree with Greg. M. Walker said minus 105. Zach said 145. Good. So everyone that said 145, you're absolutely correct. And the trick that everyone, if you weren't sure, all they did was add 120 degrees. So what about my B to neutral voltage? So plus VBN minus, where would he be? So 95, negative 95. Yep, everyone that's saying negative 95, you are correct. Let me check my math here. Yep. So all we did, right, is we just said 25 degrees minus 120 degrees. I'm going to say this was my theta VCN, and this was theta VBN. So if we drew these, let's see, minus 95, that puts us, we'll say right about there. Everyone agree that's about negative 95? So I'm just going to say that's minus 95 degrees. So if this is my VBN, who can tell me, trick question, what's the magnitude of my B phase voltage magnitude? What's my magnitude? Does anyone know? VAN, VBN equals VAN. Boom. Okay, so Jonathan and Omar pretty much got what I was looking for. It's whatever our phase voltage magnitude is, right? If this is going to be a balanced positive ABC system, so they're all going to have the same phase magnitude. And then so let's see, 145 would be, we'll just say it's up here. So this would be our VCN. Of course, has the same phase magnitude, and that's at plus 145. Now, some of you might be shaking your head or a little confused. So what we're going to do is, for balanced positive systems, we're going to draw the most basic phasor diagram, and we're going to look at the relationships. So I'm going to draw it out here because we're going to do a few more examples. Is this big enough? Can everyone see this smaller phasor diagram? Omar said yes, good. So typically, we almost always start with our A phase. Remember, our phases are always rotating, right, with respect to time or with where they're at in the cycle. Anytime we analyze relationships, we get to choose what snapshot in time that is. And typically, we always want to choose it when our phase voltage is equal to 0, the angle. So I'm going to say this is VAN, has the same phase voltage magnitude. This time he's got an angle of 0. So let's write this off to the side. For a positive ABC system that's balanced, balanced means all the phase values have the same magnitude and they're going to be spaced apart by 120 degrees. ABC means the A phase value is going to cross the x-axis first, then the B, and then the C. So this is the direction or the rotation, and this is the magnitudes and the evenly spaced out angles. So my BN and CN, we can say, we know they're going to have the same magnitudes. Our angles, so we said this is balanced. A crosses first, right, our x-axis, then B, and then C. So we know that B is going to be in this direction, C will be in this direction. The reason why I'm walking you through it is this is, I don't memorize things. I don't like memorizing things. And someone asked earlier, how do you know it's memorized? Honestly, I don't. I just get really good at deriving. So the reason why I'm explaining this to you in this manner, I'm trying to walk you through my thought process. So I know A crosses first. So if A is on 0, the next one to be hit is B. And I know if we're going in this direction because we're positive, then I know B's got to be somewhere down here. And if we're balanced, that means if there's 360 degrees in a circle, and if we divide a circle by 3 parts, we get 3 slices of 120 degrees, right? If we had a big pizza pie and we divided that pie by 3 slices, we would have 3 slices that were exactly 120 degrees. So that means I need to go this way by 120 degrees to get my VBN. And I know he's got the same magnitude. And if we're starting at 0 degrees, then I know this angle right here has to be minus 120 since this is considered in the negative direction. So we know our VBN is going to be minus 120 degrees. Jonathan Zisco said yesterday was Pi Day, by the way. Happy Pi Day. Minus 120 degrees. All right, so our very last phasor to cross that x-axis, right, they're all spinning at the same time, would be our C phasor. So A hits first, B hits second. So we know C has to be behind B. What's another word for behind? And when we talk about electrical systems, we can say C is going to be lagging B. Perfect. Good job, Alex. So we can say that our C is going to equal to either minus 240 degrees if we're going from this direction, or we can kind of simplify and say he's really plus 120 degrees this way. So our VCN would be plus 120 degrees. Now, this above example up here, all we did is we substituted 25 degrees for our theta VAN. So up there, all we did is we said, okay, if this is 30 degrees, then this is going to be 30 minus 120 degrees, and this would be 30 plus 120 degrees. So that's all we did there. This, by the way, this is true for, so far, this is true for Y or delta, as long as it's balanced and positive. Okay. I'm not going to get into negative sequence. We'll say that for a later date, later time. There's some great videos on it in the course if you want to take a look afterwards, but I don't want to take too much time. I want to really focus on y and delta. So here's where we're going to focus on the y relationships. So I'm going to draw my phasor diagram once again. Like this. We'll make it easy on ourselves, and we will start with our A phase voltage at 0 degrees where we like it. Who can tell me in the chat, why do we like starting with our A phase voltage at an angle of 0? Who can tell me in the chat? There's a really good reason for it, and knowing it really helps. So who can tell me in the chat, why do we like our A phase voltage to be at a reference of 0? What does that help us determine? What does that make it much easier to tell? Greg said, easy to see if the current leads or lags. Beautiful. So the reason why we like this, if our phase voltage A is here, if our A current is here, we know it's lagging. And if our A current is positive, right, we know it's leading. So it's just a really good way. A lot of times we'll say assume our phase voltage is at 0. That's why. Okay, so here is our phase voltages for a positive, balanced, this time it's a Y system. All right, who can tell me? I'm going to draw my line voltage in purple. Where is my C line voltage? So I'm going to say A, B, B, C, C, A. Where is my C line voltage? Go ahead, let me know in the chat. Where is my C line voltage? Where does it end up on that phasor diagram? No one know? Someone said 50, someone said 30. I'm sorry, someone said 150. Good. So careful, Kahina. Plus 30 would be right if we're talking about our A line. Tony said 30 degrees leading VCN. Perfect. Good. Good job. So we know our, and is it going to be bigger? Is it going to be smaller? Is it going to be here? Is it going to be here about the same size? It's going to be bigger, right? So this is our V. I'm going to call that VCA. Good. Mary said square root 3 times bigger, 100%. So what's my angle right here? If I measured this angle right here, what would it be? 30. Good job. So that's plus 30. Now what if I measured from here all the way to there? What would that be? What would that angle be right there? 150. Great. Okay. Can't fool you guys. Pretty easy. So which line voltage is this? And what angle is it at? Yep. That's our VA, but really we're going to call it VAB. And that's going to be at, good, that's going to be at 30 degrees. Okay. So where's our VBN? I'm sorry, where's our VBC? There we go. Where's our B line voltage? Who can tell me where's our B line voltage? Good, negative 90 degrees, negative 90. Good job. So this is VC, oops, VBC. Okay. So I'm going to say, we know this is just going to be square root 3 times V phase. And this was 30 degrees. These two have, of course, the same magnitudes, right? And we said our B was minus 90 degrees. And we said our C line voltage was plus 150 degrees. Jonathan said, so positive balance system ABC is a normal analysis way. This means we have a counterclockwise rotation. When is there a case when ACB is the method? So it really isn't an ABC or ACB method. It's all about reference. So say you were using relays to measure your three-phase voltage. You could, if you hooked them up one way, it would represent those phasors would be in different spots. And if you swapped them, right, you would end up swapping two phasors. It's kind of like when you swap directions on a motor, you swap one of the phases. So really, it's all just about reference. If a problem ever says, negative sequence, and they give you, if they say negative and it's balanced, then this guy right here would have this angle, right? These two angles would switch. So I don't want to go into it too detailed. Jonathan, if you have more questions, check out the phasor diagram module. And then if you have any questions, feel free to shoot me an email. Keena said minus 95 plus 30 equals negative 65. Why does VBC equal to negative 90? Because we have, so why does VBC equal minus 90? Because if our VBN is right here, right, we know we're going from 120 degrees from VAB, right? So VAB is 30. What is 30 minus 120? 30 minus 120 better be minus 90. Yep. So just how our phase voltages are spaced out by 120 degrees, our line voltages are also 120 degrees apart. Does everyone see that? So if I go from VAN to VBN, it's minus 120. VBN to VCN, it's minus 120. VCN to VAN, it's minus 120. If I go from VAB to VBC, it's minus 120. VBC to VCA, it's minus 120. And VCA to VAB, it's minus 120. So when they're balanced, they're all going to be spaced out evenly by 120 degrees apart. And I'm not going to draw the current because we're kind of squished here, but the current, we would always want to show it with respect to our phase voltage so we could find the apparent power. Okay, everyone good with this before I move on? And how about really quick, I'll ask one trick question. If I were to draw, if this was a negative, let me use green. If this was negative sequence, where would VAB be? What angle would VAB be if this was a negative sequence? Minus 30, perfect, exactly. So it would be right here, VAB if negative sequence. And it would still have that same 120 all the way around, right? So really your negative and positive sequence, it's just telling you, does your line voltage lead or does it lag your line current? And then what's the orientation? Okay, so the big key takeaway here is to just remember that our line voltage leads phase voltage by 30 degrees for positive. And then the opposite true is for negative. So this is the key takeaway from all of this. So sometimes a lot of people say, hey, how did you get the angle for the phase voltage when you went from your three-phase circuit to the single-phase equivalent circuit? How'd you know it was negative such and such? It's because anytime I divide by the square root of 3, so to get to my phase voltage, anytime I divide by the square root of 3, I'm also subtracting by 30 degrees to get to that angle. In other words, if I know my line voltage and I need to calculate my phase voltage, I divide by the square root of 3 to make the magnitude smaller, and then I subtract 30 degrees. So that's the big takeaway there. Jonathan said, which is why you can parallel deltas and Y. You can parallel deltas and Y. It just depends on the application. Okay, is anyone good with our phasor diagram for Y? If so, I'm going to move on to our delta system. All right, moving on. Delta. So I'm going to draw, same as before, let's draw a delta source and a delta load. I'm going to have you guys help me with both the polarity of the voltages and of the currents. This time around, we know we've got two different currents, and really we only have one voltage. So not perfect, but it'll be close enough. Okay. So this will be our source, of course. And over here on the right, I'll draw our load. Okay. Again, not the best artist in here. I don't want to take too much time drawing these out. So I don't want to take away from a good discussion, but I think that gets the point across. Okay, so here is our load. And I'm going to show our phases entering that load. I've definitely done better drawings in my day, but that's okay. Okay, so here's our load. We'll just arbitrarily say this is A, and this is B. We'll call this C. And same thing, we'll just call this A, B, and C for simplicity. Okay. And we'll say that we have the same impedance in each phase. That's just going to be our Z value. Almost anytime you're given impedance, it's almost always going to be the per phase impedance. So if they say it's a delta impedance or a Y impedance, that number, that value in ohms goes right here. Whereas with voltage and current, you can have line, you can have phase. Impedance is almost always going to be per phase. So all those formulas, Ohm's law, power, those are always going to be your per phase value for your impedance. That's one thing to point out. I get asked that quite a bit. Okay, who can help me? Let's pick on our source really quick. I'm going to say, what's my polarity for we'll call this the line voltage. So my line voltage right here, when we're just dealing with a positive ABC balanced system. Where's my plus and where's my minus go for this A terminal and this B terminal? Who can tell me directly in the chat? Who can tell me directly in the chat? So Alex says positive A. Yep. Who else? Greg said positive A minus B. Okay, good. So then what is the direction of my current, my phase current? Where does my phase current start and where does my phase current end? Alex said A to positive, B to A, B to A. Careful, Alex. Good job, Beatrice. Good job, Mary. So we know that our phase current is going to go in this direction here. So we're going to call that IBA, but we know that that is our A phase current. One thing to look out for. So when we were dealing with delta, the only time we had two letters for our subscripts, when we were dealing with Y, that was when we had a line value, right? Like up here, when we have VCA, we know that's a line voltage from C phase to A phase. But when we're dealing with delta, when we have two subscripts on our current, that's actually going to be our phase current, because this time we have a direction from B phase to A phase. All right, how about this? So where's my polarity for my voltage on my load? With A and B on my load, where's my polarity for a ABC balanced system, a positive system? Who can help me out in the chat? A to B, perfect. Yep, A is going to be positive, perfect. All right, now what about my current? Where is my phase current in my load? Who can help me? What direction? From positive to negative, from A to B, perfect. You guys are doing great. So this phase current is going to be IAB. And we know, of course, we have three separate currents, and they're all going to go in the same direction. Okay, now, where is my line current? Where's my A line current on my source? What direction is that going? That's an easy one, right? We know for the source, it's going to be leaving. So it's going to be A line current. And we know our load, we know it has to enter the load. So that's a pretty easy one too, okay? What else? Now, what's the relationship with the delta? What makes it special? What's the number one thing we always remember that's different from a Y system? Where does that square root of 3 play in? Same voltage. Yep. Same voltage. Okay, Tony said current. So which one's bigger? Is this one bigger or is this one going to be bigger? Who can tell me what's going to be bigger? So I'm seeing I line equals square root 3 I phase. Perfect. Yep. I line equals root 3 of I phase. Sure. Line current is bigger. Sure. Yep. Okay. Can't fool you guys. Pretty straightforward. Same relationship as a Y system, except this time around it's our current. So the magnitude is going to be 3 times our phase current magnitude. And that means our phase current magnitude is going to be 3 times smaller. Okay. Easy does it. How about this? If my phase current angle is 0 degrees, what's my line current angle? Mary said minus 30. Alex said minus 30. Who else? Who agrees with Mary and Alex? Who agrees? Who disagrees? Who's not sure? If you're not sure, it's okay. Let me know if you're not sure, though. It helps me know when to dig deeper. Eric said minus 30. Kahina said positive 30. Okay. Anyone else? That's the first positive 30. Anyone else agree with Kahina? Rel said not sure. Thank you. I prefer you to tell me if you're not sure. That's perfectly okay. It lets me know what your pain points are. So this is actually going to be minus 30. How do we remember this? Someone asked me in a private email last week, Zach, what's the easiest way to remember this? The way I do it is I just remember that it's backwards. It's opposite from the Y. I memorize that for a Y system, the line voltage, so VL leads by 30. And I know delta system, it's our line current this time that has that square root 3 times magnitude relationship. And I just know that they're going to be opposite. So I know that my line current this time is going to lag by 30. So that's how I personally remember it. Whatever helps you is what you should stick with. Everyone, I suggest and encourage you to draw the phasor diagrams for both delta and Y. Once you draw them once by hand, it provides a great reference for the exam, and you tend not to forget it. Okay, so we got that. Here's a good one that I bet is going to stump quite a few of you. Okay, so really quick, which phase current is this, and which phase current is this? And then I'm going to ask that really tricky question. So which one is this one right here? Who can help me out in the chat? This is going to be our B phase current, right? So that's going to be ICB. And this one right here is going to be IAB. Everyone good with that? Everyone good with those subscripts? Now, who can help me? I would like some participation. I want to know, solve for, someone said AC is missing. IAC. Oh, did I get that wrong? Let's see, BA, AB. Okay, so this should really be what? What should this be right here? Is AC missing or is something else missing? So this one's wrong, right? Or is this one right? So this is our C node. Glad you guys are paying attention. So this one right here would be IAC. And then what about the one below it? That's good, right? ICB. CB, IBA, and then IAC. Okay, that looks good. Everyone good with this, with these phase currents? Okay. So here's a trick question. I would like each of you to participate in the chat. There's 24 of you in here. If you're not sure, please speak up. Just say, hey, I don't know. That's perfectly acceptable. How do I solve for, if I know all my phase currents, how do I solve for IC? What does IC equal? How do I solve for IC? So if I know the values of IBA, IAC, and ICB, if I know their magnitudes and their angles, how do I solve for IC? So Arab said square root 3 times phase. True, but it's not the answer I'm looking for. So Beatrice said IAC minus ICB. Okay, so Beatrice, you got it right. You were the first person to get it right. Craig said IA minus IB. Careful, remember IA is actually going to be up here. Alex said IAC minus ICB. Perfect. Okay. So 2 answers from what I was looking at, from what I was looking for. Arturo said do a KCL. Yep, that's also true. So Arturo, if we do a KCL, how do we solve for RC line current? So since we have, I'm not going to go too deep into this. The circuit analysis bootcamp that should be done by the end of the week, we go heavily into KCL or nodal analysis. Essentially, every current entering a node equals every current leaving a node. So since we are solving for IC, that means we're going to set it equal to IAC since IAC is entering that node, right? So I'm going to have IAC. And then since ICB is leaving that node, we're going to subtract ICB. If you're not sure how to do this or this is confusing, the easiest way to do it is set them all equal to 0 and have everyone that's entering one polarity and have everyone that's leaving another polarity. So we can say, we'll go IAC first is entering. We'll just say that's positive. And then we don't have any more entering. We have 2 leaving. So ICB and IC will be negative. ICB and minus IC. And then we just set it equal to IC. So we can say IC equals IAC minus ICB. So if you're not good doing it this way, just set them equal to 0. Make all the ones entering one polarity, make all the ones leaving one polarity, and you'll get the relationships just right. So likewise, now I know my line currents over here on my load. I want you to help me solve for a phase current. So let's pick on, we'll pick on this one right here. How do we solve for IAB? What would we need to solve for IAB? Okay, so we know all the phase currents. And we'll say this is A, this is C, and that's B. So this is ICA, and this is IBC. Alex said IBC minus IB. So if we're solving for IAB, we would have IBC minus IB. Yep, we will. That is definitely one way. So that is IBC minus IB. And then the other one is we could do it, we could look at it up here too, couldn't we? We could say IAB is going to equal to IA minus ICA, right? So we could say IAB equals, actually no, we would have IAB equals IA plus ICA, right? Since they're both, these two currents right here, IA and ICA are entering this node. So we can set it equal to the only current leaving that node, which is IAB. Okay. Everyone good with these two right here? You'll notice that the relationships are different between the source and the load. So anytime you're asked to do this, you have to derive it on the spot. Sharab said, Zach, your notes at the bottom are not legible. How about that? Is that a little better? So if we were to solve for, look at this. If we solve for our A phase current here is IBA, we would have the opposite relationships as our load and our source. So that's just one thing I want to point out. Your load and your source current relationships when you do KCL are going to be different. So make sure you do those separately. All right, let's talk about phasor diagrams for our delta system. I'm not going to spend as much time here as I did with the Y system because I think we got the hang of it on the Y system. I'm just going to go ahead and draw out the general relationships because I really want to make sure we get to three-phase circuits, and we're actually already at like an hour and a half. Okay, so our delta system, I'm going to go ahead and say this time I'm going to be drawing my currents, right? So I'm going to say this is my, I'm just going to say, I'm going to call it little a for phase voltage, okay? Or I'll just do a phase. I'm not going to worry about the other subscript because if it's a load or a source, right, that orientation would change. So I'm just going to say a phase. And then I'm going to have my B phase current right here. So I'm going to say A or IB phase. And this one right here is going to be my IC phase. Everyone good with this? Make sure it's legible. So we all know, first of all, this is a positive, balanced ABC system. So we know since it's balanced, we know the magnitudes for all phase currents are equal, and we know they're going to be 120 degrees spaced apart. So here I have minus 120 degrees. Here I have plus 120 degrees. And since it's a positive ABC system, we know that our B current lags our A current, and our C phase current lags our B phase current, excuse me. So now I'm going to pick a different color that's going to stand out. We're going to draw the line currents. So we said that they are backwards, right? The leading and lagging relationships are backwards. So who can tell me in the chat which line current is this? So this is going to be, yep, our A current. I'm going to use L just to signify line current. And that means that this guy right here is going to be our IBL. And this guy right here, right at 90 degrees, he's going to be our ICL. So we know that we lag by 30 degrees, right? And we know that each of our line voltages, each of our line currents, they're also going to be 120 degrees apart. So from A line to B line current, we have minus 120 degrees. And from A line current to C line current, we have plus 120 degrees. Okay, everyone good with this? Otherwise, I don't want to spend too much time. A lot of this we could talk forever about, and I really want to get into three-phase circuits. All right, moving on. Delta versus Y impedance. We'll touch on this really quickly, and then that'll be the perfect build-up for our three-phase circuits. So I'm going to go ahead and draw a delta system on the right, or on the left, and a Y system on the right. And for the sake of simplicity, we're just going to talk about a balanced system. So all of our delta impedances are going to be equal, and all of our Y impedances are going to be equal. And that's just going to simplify the impedance transformation formula quite a bit. Do be familiar with solving for the transformations if the impedances are not equal. It's very possible to get a question like that on the exam. And if you do, don't panic. It's pretty straightforward. You're just going to have to use the more complicated formula and not the one that's just simplified. So I'm going to say that these are my Y impedances. So each one of these impedances, we're just going to call it a complex Z sub Y. They're all equal in value. And each one of these over here, we're going to call this our complex Z with a delta subscript, and they are also all equal in value. So if we want to go from delta Z to our YZ, then we can use the formula that says our Y impedance is going to equal to, let me see here. It's going to be our delta Z divided by 3. So that means that each of these values over here are 3 times larger our delta Y. So when we go to delta from Y, we're going to multiply this time. So we're going to have our delta Z is going to equal to 3 times CY. Now, this is one, I just usually have this in a reference somewhere. You probably even heard me flipping the page. If you can memorize that the delta is 3 times bigger, then go for it. If not, this one's pretty easy. As long as you have it in an easy to find spot, you're pretty good to go. So our delta Y would be 3 times smaller. Okay, any questions on this before we move on to our 3-phase circuit? And of course, if this was not a balanced system, so this is for balanced only. Someone says, can you please talk about unbalanced systems? Tony, I would love to. Unfortunately, we're already an hour and a half in. I don't want to go too far into it. I would say review the Phasor module. It spells it out pretty clear. The videos are really straightforward. And if you have any questions, feel free to email me after you watch that. I'd be happy to answer them. But I don't want to spend too much time. Today, we're not going to focus on unbalanced versus balanced. All right, any other questions with our simple balanced delta and Y impedance transforms? All right, here we go. 3-phase circuits. Someone go ahead, jump out in the chat. Do you want to do YY, delta delta, or a variant of delta Y? Go ahead, pick it in the chat, and we'll just we'll make it very impromptu. So, Rel and Alex. Wow, everyone wants delta Y. Look at that. Okay, so clearly everyone wants delta Y. So let's talk about that. All right, delta Y. Let's say we've got a delta source over here. So typically, anytime you're doing you're solving a 3-phase circuit, you always want to go from the 3-phase circuit to a single-phase equivalent circuit. That's almost always the goal. So let's say we have some delta Y source, and we'll call this A, B, and C. And let's say we have a line impedance, right? So I'm going to call that Z line. And we have, it's going to be a balanced ABC system. So our line impedance is going to be the same in each phase. And then next, we will have a Y load. I'm going to go ahead and plug in some values. Actually, you know what? Let's draw this upside down. So who can tell me what's the easiest 3-phase system to work out on paper? Is it delta delta? Is it delta Y? Is it YY? Is it Y delta? What's the easiest? YY, exactly. Perfect. Okay, good. So anytime we're dealing with anything other than a YY system, we want to make it a YY system, right? And who can tell me why? Why is a YY system easy to work with? Why is that the goal? Who can tell me? Alex said single phase, same current. It is going to be the easiest to get into a equivalent single phase circuit. Okay, great. So this is our third Z line. A good practice too is you'll see a three-phase voltage drop too, say a delta Y. That's very common. So I'm going to call this my Z load. So these are all going to be the same. And I'm going to pick some values here. Let's say our Z line is, we'll say 2 plus J 5 ohms. And let's say our load is 10 plus J 20 ohms. Really reactive load. Who can tell me, is this a leading or lagging load? Quick question while I finish this. Who can tell me, is that leading or lagging? And we're going to use a good. Everyone said, oh, careful, Eric. That is going to be a lagging load. Good job, Alex. Good job, Rel. We're going to go, I'm just going to pick 480 volts. We're going to say this is a three-phase. So the problem I'd say a three-phase 480 volt delta connected source. Notice I didn't say line or phase, right? Anytime the problem says three-phase, the next voltage, unless it says phase, you assume it's line, okay? So you're going to assume that's going to be your line value unless it says the phase to neutral or the B phase to neutral voltage. Eric says, that's what happens when I don't look at my cheat sheet. Mary said, why lagging? Lagging because our impedance angle is positive. So if our impedance angle is positive, we know our power angle is positive. So our Q is positive. Okay, so we have line-to-line voltage of 480 volts. How about let's solve for the voltage drop across the load. So we'll kill two birds with one stone. We're gonna do a three-phase circuit and we're gonna do a voltage drop problem. So I wanna know, okay, we've got a three-phase 40 volt delta source is connected to a Y impedance that equals 10 plus J 20 ohms per phase. This is how you're likely gonna hear the problems. And it's connected through a transmission line that has a 2 plus J 5 ohm impedance. So that's our line impedance, okay? What is the voltage drop across a load? So what is VZ load? All right, what's the first thing we want to do? First of all, what's the first thing we want to do? And essentially, what value is missing in this circuit to know the load? In other words, if I had one variable and if we combine just one more variable, but with what we already know, we would be able to find this voltage drop. What variable would that be? And what is my first step I would have to take to solve this problem? Who can tell me? Good, current. Everyone's saying current. Great. Yes, exactly, right? Y, Ohm's law, V equals to IZ. So if we knew that current, we already know the voltage, we know the impedance. And everyone else is saying change line to neutral. Great. Single phase equivalent circuit. Yep, perfect. So in order to change this to a single phase equivalent circuit, we need to model this as a Y source, don't we? Okay. So there is no phase voltage on a delta, right? They say phase voltage equals line voltage, but I don't like that because it's not really correct. We only have our delta voltage. We have the voltage across two phases. We have our line voltage. So when we do an equivalent Y source, right, this doesn't exist in real life. I want to make sure everyone understands that. We're just doing a model on paper. We're saying, okay, if I made up a Y source that had the same characteristics such that it would have this line voltage, then I could find the phase to neutral voltage, then I could find my current, then I could find my voltage drop. So let's go one step further. I'm going to say this is an angle of, I'm going to make it tough. This is minus 12 degrees. And that's our VAB. Okay. Who can tell me what would our Y VA to neutral be? You don't have to do the math. You can say divide by or multiply by square root of 3. That's perfectly fine. Omar said 40 divided by square root of 3 equals 277. Okay. So we'll say Let me get my Phasor hat here, and I missed it here. So 480 volts divided by root 3, and what's my angle? You don't have to do the math, just say it in the chat. Omar, you got it again, minus 42. Does everyone see where we got this minus 42 voltage? This angle? Does everyone see that, right? Because our phase voltage lags, right? So if this is our phase voltage, we know this is our line voltage for a Y system. So we know this is a 30-degree difference. So not only do we have to adjust the magnitude, we have to adjust the angle. So since this angle was negative 12, if this was minus 12, then this would be minus 12 minus 30. 42. Rel said, oh yeah. I'm telling you, please, everyone, draw those Phasor diagram relationships, and I guarantee you this stuff will stick. Okay, beautiful. So we found our plus minus voltage right here, right? So I'm just going to draw it to look like this. Let's say here's A. Here's our neutral. And we now have Z line. Here's our Z load. And I'm going to erase that really quick. Perfect. How does this look to everybody? So essentially, to find that single phase equivalent circuit, all we had to do, because we can connect, there's a neutral point here, right? So we can model, right? It doesn't have to be connected for us just to model the relationships. It's perfectly fine. So is everyone okay with me saying this is going to be, this voltage right here will be plus 480 volts divided by root 3 at an angle of minus 42 degrees. And this is my same 2 plus J5 ohms for my line impedance. And this is my same 10 plus J20 ohms load impedance. Everyone good with that? So here's what I'm going to do. We're not going to solve this all the way. We're going to do a couple of the steps, just the variables, because we're getting close to 2 hours, and I want to cover more examples of the three-phase circuits because I feel like that's really, once you get that, you got it down pat. So let's just solve this using variables only. We'll call this our I. How would I solve for my I in this case? How would I solve for the I, and why am I solving for the I? Who can help me? Go ahead and write it directly in the chat when you're ready. I would be V over Z. Okay, I'll accept that. What would my V be? What would my Z be? Let's go with that. Eric said Z equivalent. Good job, Eric. You know I love those subscripts. Tony said I equals E over ZT. I'll take that, Z total. Kahina said V equals I times, in parentheses, Z plus Z line. Sure, I'll take that too. Good. So let's say this would be 480 volts at minus 42 degrees with the magnitude square root 3 times smaller. And our Z would be 2 plus J5 ohms, that's our line, plus 10 plus J20 ohms. Now, I'm going to take it one step further. Haha, good, Alex. Alex said voltage divider. Fantastic. Yep, you definitely could have taken a shortcut. I'm going to go one step further. What if the problem asked for our line-to-line, find our line-to-line load voltage? In other words, if this was a three-phase motor, what voltage would that motor see if we took a volt ohm meter and we measured from here to here? We'll take it one step further. I think that'll further help us demonstrate the point, and it'll let us play with those angles a little bit more. So I guess we'll go ahead and we'll work this out anyways. It won't take about a second. Who's got a calculator? Go ahead and work this out for your current. Omar, man, you are on top of it. Look at that. Omar already got it. So Omar said 9.9 amps with an angle of negative 106.4. I'm going to check it really quick. Anyone else, feel free to check it with us. I'm going to check it really quick, and then we'll solve for a voltage drop. So I've got a magnitude of 480 volts divided by the root 3 at an angle of negative 42. And all of that is being divided by both of my impedances. So 2 plus J5, and then plus 10 plus J20. And my calculator's in the rectangular mode. I'm going to swap it over to polar. And let's see. Omar, I got a slightly different answer. I got 0.36 amps. Let me just double check this one more time. 480 volts divided by square root 3 at an angle of negative 42. Yep. Okay, divided by 2 plus J5 plus 10 plus 20. So I got a slightly different answer. Did anyone else get a different answer too? I just want to make sure I am not doing this correct. Greg said you got 9.9 as well. Okay, let me try this one more time. So 480, I'm going to use parentheses this time. 480 divided by root 3 at an angle of negative 42, okay, divided by 2 plus J5 plus 10 plus J20. Okay, I don't know what was up last time. Yep, 9.99 amps at negative 106.35. So I'm going to leave that at 4. I'm actually going to round this to 10 amps since it's 9.99. So let's just go ahead and round that to 10 amps. So that means this amps right here, if we go back to our three-phase circuit, that literally is this current right here, right? That's our 10 amps at an angle of negative 106 degrees. So we use that single phase equivalent circuit to solve for that. All right, why do we solve for that amps in the first place? What does that current give us? Right, it gives us the voltage drop across our load. So we're going to multiply that by our load impedance, which is 10 plus J20. So I'm just going to go ahead and hit multiply in my calculator by 10 plus J20. So that gives me 223.5 volts at an angle of negative, I'm going to say around negative 43. Omar and Greg, you guys good with this? So we just solved for this, didn't we? Good. Seeing a lot of yeses in the chat. So we just solved for this right here. You'll notice, even though I already have the answer, I'm not just drawing this out to show you guys. If I was solving this problem, I would have taken every same step. I would have drawn everything out like I just did. I would go ahead and fill in exactly where I got that voltage. Never feel like you don't have enough time to do this. It takes just seconds. Because now, are we done yet, or do we have one more step to do? And writing it down here alerts me to the fact that we're not quite done yet, right? The problem we said asks for our line-to-line load voltage. So we just found this voltage right here. And what we really want is this voltage right here, don't we? So how do I go, if this is my voltage right here, how do I go to my line voltage? Alex said times square root 3. Okay, what if the problem said find the A to B line to line load voltage? So now we don't just want magnitude, we also want the angle. So now what do I have to do? So this is single phase. What do I have to do? So we know we have to, good, Kahina, fantastic, Greg, fantastic, Alex, fantastic, bingo, you guys are on it. So not only do we multiply the square root of 3 times our magnitude, we know we've got to shift up, right? We've got to lead again by 30 degrees. So I'm going to say my calculator, square root 3 times 223.5, and I get 387 volts. I'm just going to round it to the nearest volt. And of course, I get 43 minus 30, which is just negative 13 degrees. So the answer would be 387 volts at an angle of negative 13 degrees. Is everyone good with that? So we did a line to phase voltage transformation and then a phase to line voltage transformation. Is everyone good with that? Does everyone see why we subtracted 30 degrees to get to the equivalent circuit, and then why we added 30 degrees to get to our line voltage? Is everyone good why we modeled a Y source even though we were working with a delta source to find that current? Good. Good. Eric said, can you discuss the negative 30 and then the 30? Sure. I'm going to fly up here really quick to my phasor diagram. We said on a Y system, so this is a little busy here, but on a Y system for a positive balanced Y, our line-to-line voltage leads our phase voltage by 30 degrees, doesn't it? So my A line voltage leads my A phase voltage by 30. My B line voltage leads my B phase voltage by 30. And same is true for my C line voltage and my C phase voltage. Are you good with that? So Eric, we started out with our line voltage, right? And then to get to our phase voltage, not only did we subtract 30 degrees because now we're going in this direction, but we also divided by the square root of 3, right? To get the magnitude? Good, okay. And then we just did the opposite when we went back from phase to line. And an easy way to remember that too, because a lot of people are always asking for mnemonics, is anytime you know that you need to multiply by the square root of 3, remember that you need to add by 30 degrees for Y voltage, right? And then anytime you need to divide by the square root of 3, just remember that you're going to have to subtract by 30 degrees. How about this? What if the answer, or I'm sorry, what if the question said, what if we were interested in finding this voltage right here? So this is plus VBC minus. What if it asked, okay, I gave you the A line voltage of the delta. I gave you both the magnitude and the angle, but I'm actually interested in finding the B line voltage of the load. How would we find that? There's two different ways we could have taken it. Both are perfectly fine. One involves shifting the angle in the beginning. The other involves shifting it at the end. So at the end, since we already have A to B, Kahina said VAB plus 120 degrees. Yep, perfect. Would it be plus or would it be minus? Would it be plus or would it be minus? Let's draw it out. Same magnitude, yes. Right, it would be minus. Yep, exactly, Omar. So again, how would you know? How would you know? Do you want to memorize that? Right, it's tough to memorize. All I would do is say, okay, I just solved for my load AB voltage. It's minus 13. So I'm just going to draw it here. So this is VAB, right, at theta equals minus 13 degrees. And I know if I'm interested in finding our V load B to C, that's really my B line voltage. For a positive ABC system, I know it's got to be probably like right here maybe. And we would have to subtract 30. Oh, excuse me, subtract 120. So it would just be minus 13 minus 120, I get minus 133. So our theta would be minus 133 degrees. Is everybody good with that? And as extra credit, instead of shifting the angle at the end, is there an angle we could have shifted in the beginning and solved directly for our B to C load voltage, right? Couldn't we have modeled our equivalent circuit? What if we modeled it off this voltage right here, plus to neutral, and then drawn it with this impedance, right? And this impedance. So we would have found the phase voltage entering here, right? We would have found that voltage drop plus to minus, and then we could have converted to our three-phase voltage here, right? Yep, exactly. Kahina, you said V B to N. So how would we do that? How would we, what would my V, how about what would my V B to C be? We'll start with that. What would my magnitude be and what would my angle be? Based off what we already know. Who can help me? For a positive ABC balanced system. What would this angle be? So we know our VAB, right? Our VAB, our A line voltage is 480 volts at an angle of negative 12 volts. Sorry, excuse me, negative 12 degrees. What would my magnitude for VBC be, right? So this is VBC, which is really our B line voltage. Magnitude would be, yep, 480 volts, Alex, and you said minus 132. So minus 12 minus 120, right? So that would be minus 100 and yeah, 132, negative 132 degrees. Careful, Greg said at 102. Careful, Greg. Alex, you got it. And Omar, yep, fantastic. Great job, Omar. So we could have done that. Or what about, what would our B to N voltage be in comparison to the single phase circuit we already have? What would our VBN be? How can we shift it from here? What would that be? 480 volts, right? Divided by root 3, same magnitude. What would my angle be this time? Yep, Mary, negative 162. Fantastic. Does everyone see how Mary got that? Beatrice, good job too, negative 162. Does everyone see how everyone's getting that? Perfect. So take a look what Alex wrote in the chat. If you're not sure yet, Alex said 120 minus 42. That's true, Alex, but the best way you want to think of that is always have the phase, or always have the voltage angle first, and then have your shift, your lag, your lead after it. You are likely to make less mistakes on leading versus lagging this way, but that's still absolutely correct. So yeah, so all we did here was we went from AN neutral, right, to BN. We saw this shift 120 degrees. Okay, it's been about 2 hours, but I'm still okay if we can cover a little bit more. There was a few more things I want to talk about. I'm not going to have time to talk about leading and lagging because I want to talk about a few more points for three-phase circuits, but we'll talk about for 15 more minutes. And then I know everyone's tired, myself included. Do I have any questions about the example we just did? And if not, do you have any other questions? Maybe delta y, y, delta, delta. We won't do another worked out example because that will take too long, but I would be perfectly happy to talk about the relationships and we can draw out the relationships. Okay, how about this? So what if you had a delta system, and to make the best use of our time, I'm just going to draw it a little quicker and it'll come out faster. So if I had a delta system, okay, So here's our impedance, and it's balanced and it's positive. So we know our voltage magnitudes are equal. We know our impedances are equal in both magnitude and angle. And what if we knew our line current? So I'm just going to say, if we knew our line current, call this A. Another thing too, sometimes you'll see like little a, big A. Sometimes different authors will use little a for the source, big A for the load. Really, that's just to indicate direction. So you ever see something like little a, big A, they might be saying from source to load or from load to source. So don't let that confuse you if you see that. That's just indicating direction. So let's say we know our line voltage and we know our delta impedance. But what we're interested in finding is our line impedance. How would we do that? And we won't use numbers. We won't do an actual example because that'll take too long, but this will give us some quick practice with a quick source transformation. So what if we wanted to find our line impedance? Who can help me out? What do I need to know? Someone said to convert delta to one phase Y. Sure. On my source or on my load? On my source or on my load? Both. Exactly. So here's our source. Here's our load. Who can remember? We'll draw it like this. And apologize, I know this is a crude sketch. I'm just trying to make the most use of our time, so forgive me. But I think it still does a good job at demonstrating the point. So let's say that this is our source transformation. This is our load transformation. We still have our line impedance. Trick question. Has IL changed? I'm sorry, has IA, tongue twister. When we do that transformation, is this the same value or does that change? Does that change in magnitude or does it change in angle or is it exactly the same as above? Is that line current going to equal here? Same. Fantastic job, Omar. So IA is going to equal to IA still. And someone just talked about earlier on, I think when we first started, they were asking, what if you don't know if it's delta or Y, right? How about that? Right? So regardless if this is delta or Y or if this is delta or Y, your line current is going to be your line current regardless. Okay, so we did a source transformation. Who can tell me what's the next step? We need to go from a three-phase circuit to a. What kind of circuit do we need to go to next? Single phase, right? Single phase circuit. Okay, Zach, what would be the first thing we would need to find? So essentially for a single phase circuit, we're doing this, aren't we? So a single phase circuit, we're looking at this right here. Does everyone see that? This is essentially, when we say single phase circuit, we're looking at just one phase, right? Where here is our neutral. Okay, good. So we need to find two things, don't we? Who can help me? What are the two things we need to find? Find the source phase voltage and the load phase impedance. Fantastic. Omar said phase voltage. Sure. Omar, Zach, and Alex, why don't you help me? What would my phase voltage be? And what would my load voltage be? And remember, we don't have any numbers, so feel free to just write it directly in the chat. Remember, we're trying to find this pesky Z line. So we know, we don't know our Y load, so it's going to be Y load. Omar said 277 volts. That would be true if we were using the same numbers as last time. Source voltage equals V. Kahina, would we need to change this voltage? So if we knew this voltage, so we know plus minus V delta AB, I'm going to call that. So we've got that. Good. Greg divided by square root 3, you're right. Alex and minus 30 degrees. Fantastic. Mary and Zach, fantastic. You guys got the whole formula in the chat. I am impressed. Good job. Yeah, you guys are absolutely right. So I'm just going to say this is still my A phase. We'll call this plus minus. I'm going to say VA neutral will be my magnitude, right? That's what that bracket's for, of my delta VA divided by square root 3 at an angle of, we'll say theta, getting kind of crazy here with these subscripts, theta V, that should be AB, VAB minus 30, okay? Kind of hard to see, apologize for that. My current is still IA, right? That is unchanged, so IA is still the same. Okay, that leaves one more, right? Who can help me? How do we get this guy? So we said we knew this impedance right here. How do we get this guy? We know we got to do something to our delta impedance, but we're not sure what it is. Mary said delta divided by 3. Kahina said delta divided by 3. Perfect. And Zach J said Y phase load impedance equals Z delta divided by 3. Fantastic. Great. So how do we find this guy right here? How do we find the ohms of our line impedance? What's one of the biggest formulas we can always go back to if we're unsure of what to do? What's one of those most fundamental formulas we always, perfect, Ohm's law, V equals to IZ. And Zach, I'm so glad you said V equals to IZ, you too, Kahina. I want to make sure everyone gets away from this. V equals to IR. We know that complex V equals complex I times complex Z. So jam up job, fantastic job, guys. So we know we're solving for our Z, right? I know I don't have to ask you guys that. So we have our voltage divided by our current. We know our voltage value. We'll just leave that as this guy right here. And we know our current value. That's this guy right here. However, what do we got to do over here? We really have to set that equal to what? Z line plus ZY load. Everyone good with that? So really, our Z line would be our A to neutral complex voltage divided by the same current. Can everyone see that? Divided by the same A current that has not changed one bit from the original problem minus the known Y load impedance. Bingo. Is everybody good with that? So we could solve for that line impedance once we know our equivalent A phase to neutral voltage, both magnitude and angle, right? We would need the angles. Does everyone see why we would need our angles? Because we would want to find our line impedance in terms of R line plus JX line, right? And if we didn't know the angles, we would only know our magnitude, which would really just be the sum of the squares. And we wouldn't know what the individual values are. Does everyone see why that? That's another way we can address when to use the angles. Now, final question. I'm going to scroll all the way back up here to the top. Trick question. Do we need to do anything different? Think about this for a second. And it could be a trick question. We went from a delta-delta to a YY to an equivalent circuit to solving for our line impedance right here. So when we go all the way back, does anything change to that Z line impedance in ohms? Do we have to do any kind of transformation to that? Do we have to go back to a delta? Do we have to go back to Y? Good. Greg said nope, same value. Alex said no. Tony said angle. Careful, Tony. Zach said no. Sawarb said no. Fantastic. Good job. Good job. Kahina said no. Good job. Good job. What if we knew our line impedance, right? What if we knew this one, but we didn't know our delta? Then we wouldn't have done a source transformation until the very end, right? So here, when we were solving for our line impedance, but we knew our delta impedance, we did a Z delta to ZY transform, right? However, if we didn't know our Z delta, then we could have done the same formula. This same relationship here would have given us our ZY load, right? And then we could have just done a ZY load to a delta transform. We could have taken that and moved that to a Z delta load. Does everyone see that? If they asked us to solve for the delta load impedance instead of the Y, or instead of the line impedance? Does everyone see that? How we would have done that transformation at the very end? Craig said, so in that case, you would be finding the YZ, so you need to multiply by 3. Exactly, Craig. Actually, I think we would be, yep, you're right. We would be multiplying by 3 because the delta load is 3 times bigger than the Y load. Perfect. Eric said, so is a takeaway that line values stay the same independent of delta or Y? Eric, yes, but it depends on how you think about it, because remember to solve for, let's talk about that actually. So Eric said, is the takeaway, I'm going to do a question, is the takeaway that line values stay the same independent, and I'm assuming you mean line current, Eric. I'm assuming you mean line current. Let me know if you're not, so I can adjust that. Line current stays same. Independent delta Y, current and Z stay the same. So yes, for the line, yep. Our line impedance would not change as long as it's per phase, right? I doubt they would ever say a total complex line impedance, 3-phase line impedance, because that's just silly. I've never seen that. And our line in this particular example, yep, independent of delta or Y, and then for the source, and delta or Y for the load, yep, these two would stay the same when we go from 3-phase to a single phase. And Kahina said, when the Z loads have different values, shall we proceed differently? Yes. So our impedance per phase, I'm going to say Z per phase, are going to be the same for a balanced system, or really a balanced load would be more accurate. And they're going to be different for an unbalanced load. And when we said, let's see, delta Z is 3 times bigger than YZ, look at that. So I picked up a new way to remember that tonight. Where this comes from, Kahina, it comes from a much more complicated formula. It's not really too complicated. We just use the individual impedances. And I'm not going to go into that tonight because we might run in circles, but review, I think it's in the 3-phase circuit module. If you can't find it, shoot me an email. I'd be happy to send you a direct link. But the formulas for the unbalanced load, you can find it in there. And there's nothing to it. There's no sweat. Uh-oh, Omar said sound loss. Can everyone still hear me? Oh, kicked back in, I guess. I think that might have been on your end. Keena said, okay, I have it in my sheet. Good. Okay, so we've gone a little longer than 2 hours. Like I said, I knew we really weren't going to have time for leading and lagging, but we covered pretty much all the important stuff that I really want to talk about. We covered power, covered delta, we covered Y, we covered the phasor diagrams, and we covered our 3-phase circuit examples. Before I jump off the screen share, does anyone have any last minute questions relating directly to anything that we talked about that we haven't addressed or that you had lingering? Omar, in all caps, shouting at me, said, Zach, out of topic at voltage drop, calculation at transmission line, Z efficiency or Z effective is required to be included always. So careful, Z effective is a approximation of line impedance that they use for calculating the ohm value of a ohm per length times a length value. Typically you get the effective impedance just to find the total value in ohms, right? Because effective impedance is usually our ohms per 1,000 feet or 1 kilometer. So typically if we don't have a Z effective, right, they might say find 5 AWG, we'll say 8 AWG of like copper. They'll give you the characteristics, right? The power factor. You have to look up the effective impedance, and you have to multiply that by your length to get just the ohms. If they give you just the ohms, like what we were working with tonight, then they're not going to give you the characteristics of the wire. And if they do give you the characteristics of the wire, then it would be a red herring. Omar, does that answer your question? Kahina said, do we need, thanks, you're welcome. He was putting all those caps at me, shouting at me, trying to get my attention. Kahina said, do we need to add 30 degrees at each time we calculate V line? Kahina, if we are calculating V line off of our phase voltage and we're working in complex numbers, aka we're not using just magnitudes, then yes. But that's only when we're going back and forth between phase and line voltage. Back to these phasor relationships right here. Right? These guys are right here. The difference between the red and the purples. Kahina, does that answer your question? Arturo said, what would happen to load if at the source a short occur at one of the legs? You would have a line-to-line fault, wouldn't you? And we know a line-to-line fault, so that's a good question. Yeah, it's somewhat related. I'll take it. So Arturo asks, okay, so let's look at that. Sorry, I'm not trying to make you guys dizzy. Say we had a Y load, say we had a delta load. If I had a short circuit right here, or if I had a short circuit right here, right? Short circuit. Then these would be an example of, that's an H, isn't it? I'm getting tired. Short circuit. So these would be example of what? These would both be a line-to-line fault. And we know that a line-to-line fault, we need to solve it with symmetrical components, which is a whole nother animal. Arturo, does that answer your question? Mary said, for a negative sequence, is our line voltage still leading? Okay, I'll talk about that really quick. So let's draw 2 phasor diagrams. And to save time, I won't draw every single individual line and phase. I'll just do the A line and A phase. So, okay, let's say this is ABC. So everyone knows ABC is the same thing as positive, and ACB is negative. Sometimes it's ACB, sometimes it's BAC, right? So let's draw our phase. We'll keep our phase voltage unchanged. We're going to draw that in blue. So these are going to be both our V phase at 0 degrees. Okay, everyone okay with that notation? V phase at 0 degrees. So let's say these are Y systems. So this is Y, right? Since it wouldn't change for a delta. So if it was a delta, the order that they cross the horizontal would change, or the rotation direction would change, but Since there is no difference between phase and line, we have no difference in the leading or lagging relationship. I just want to clarify that. So really quick, ABC positive, if this is a Y system, who can tell me where my line voltage would be? And if it's negative, who can tell me directly in the chat where my line voltage would be? Go ahead, write it directly in the chat, and you will help me answer Mary's question together. So go ahead. How about my positive ABCY? Where would this line be? Mary said plus 30. Fantastic. Okay, so here's plus 30. So I'm just going to say VL. I'm going to say 0 plus 30 degrees. That way, if you're going back in your notes, you know if this changes, you have to still change that there. So we know that VL is leading, right? VL leads. Okay, so let's think about this. This is a counterclockwise, right? Which means we're going this way, right? If our rotation direction changed, who would cross the x-axis first, phase or line? See that? In ABC, we're rotating this way. So that means my line voltage is going to hit first and then my phase, right? So in other words, if my line voltage was if this was my line voltage at 0, my phase voltage would be down here at minus 30, right? But since we're looking at it when our phase is at 0, he's going to be leading. And ABC, it rotates negatively, but typically when we draw it on a phasor diagram, we still assume the same rotation angle, but we just draw the relationships backwards. So we would have it like this. So now our VL would be at 30 degree or at 0 minus 30 degrees. Does everyone see that? Keenan said 30 degree lag. Exactly. Now VL is going to lag. So there's two ways that we could really represent the negative phasor diagram. And the most important, so relating to the PE exam, they're usually not going to say, they're usually just going to give you a phasor diagram like this and say a balanced system. It would actually, let me just redraw it because I think that's actually a really good point. So on the PE exam, if you get asked like a really straightforward, look at that, look how easy that is. I love that. If you get asked a really straightforward question, it's going to say, is this a positive system? Is this a negative system? It's going to say for the below system, is it positive, negative, Y, or delta? Assume it's balanced. If you saw something like that, and those two could be anywhere, right? But VL, regardless of where they're at on the phasor diagram, right? They could be over here even. VL will always lag it. You know that this is what? You know that it would say, is it a Y positive? Is it Y negative? Is it delta positive? Is it delta negative? Right? We know that it's got to be a delta negative, right? Why? Because VL is lagging. And why? Because we have a difference in phase voltage and line voltage. Does everyone see that? So really, this phasor diagram, they're still rotating counterclockwise, but now our phase voltage hits first and our line voltage hits second. Whereas in our positive up here, our line voltage would hit the x-axis first, followed by our phase voltage, right? If they're coming this way. So there's really two different ways to represent this. And if we showed a true, and I don't want to lose anyone, I don't want to get into too much theory, but there's a couple of different ways these problems could be shown. If we were to represent a true negative rotation and we showed the rotation going clockwise this time, guess what? My phasor diagram would look exactly the same, wouldn't it? Does everyone see this? And I really hope I don't confuse everyone. I hope I don't confuse you. This would be at 0 plus 30 because look, phase voltage is going to cross the x-axis first before line if we rotate clockwise. And if we're rotating counterclockwise, my V phase is still going to cross the x-axis before VL. So that's just a really nuanced point to be aware of. In my opinion, you're more likely to see it like this But another way the PE exam might say it is, what if they don't say positive or negative? What if they say it rotates counterclockwise? That's code word most of the time for positive. And if they say if it's just rotating clockwise, that's code word for negative. So there's a lot of different ways these can be represented. Arturo said, following on my question, source will operate at what percentage? The load will stop or continue to operate. Oh gosh, Arturo. That would be a really in-depth short circuit analysis on symmetrical components on a line-to-line fault. Essentially, if you got any kind of real load on there, you're going to trip a breaker, right? Because if you short, you're going to draw max amps, and max amps at that phase can deliver. Well, 9 times out of 10, it's going to exceed the rating of the breaker, the trip settings. So you're going to pop that breaker big time. You hope you do. If you've got a protection engineer worth his salt, he set it up correctly, and you're gonna pop that breaker to protect that equipment. All right, it's about 10:56. Wow, going on about 2.5 hours. Any more questions? If not, I will hop off my screen share, and we will. I'll say goodbye, and we'll sign off. Okay, guys, I'm gonna pop off really quick. So I'm gonna start video and stop. You're welcome, Kahina. You're welcome, Jonathan. Let me see. Oh, I lost the chat. All right. So what I'm going to do, thank you guys. I hope you got a lot out of this. You can tell my voice is starting to go again. If you have any other questions that you want to go more in detail about what we talked about today, feel free to shoot me an email and I'll get to it. I'll work it into my schedule for the day. What I am going to do is, this session was recording. So just like last time, this entire presentation will be available in the course under the bonus material. It'll be up there probably by midnight tonight on the East Coast, so it'll be ready for tomorrow. And all of the notes that we took today, very, very neat, very cool. I'm going to include a link to the PDF, so make sure you click it and download it. And feel free to add it to your reference binder. Feel free to go over those examples one more time. You might find a couple things that you're not sure about too. So I will include the link. I think that's really valuable. Frankly, it's one of the reasons why I use this note-taking software, because I can just export the whole thing as a PDF and send it to you guys. I think it's really valuable. It's a great tool. So that's about it. We will meet again the same time next week, Wednesday, 8:30 p.m. on the East Coast. I'll send out another invite by Friday, and I will know what lesson we're going to talk about then too. So thank you everyone so much for joining. I hope you had a great time and learned quite a bit. So we will see you next week.